Welcome back to this NPTEL course on principles of polymer synthesis. Today is lecture number 19 and we continue to talk about the principles of chain copolymerization. To recap, the last class we have been talking extensively about how to derive the composition of copolymers, both the instantaneous copolymer composition with respect to the comonomer composition or comonomer feed composition, and also with respect to percent conversion, how the comonomer feed composition might drift. It might drift because both the monomers do not have the same reactivity. So, the monomer which has more reactivity, it goes in more into the copolymer, it will be preferentially going into the copolymer compared to the monomer which has less reactivity. So, then in effect what will happen is that the comonomer feed, remaining comonomer mixture, that will become richer in the component which is less reactive, and so with time then the comonomer feed composition will drift. And since the copolymer composition, it depends basically on the comonomer feed composition also, because there is this ratio of M1 and M2, there is this ratio of M1 and M2. If you look at this particular paper here from the previous expression that we had, dm1 divided by dm2 equals m1 divided by m2 into r1 m1 plus m2 divided by m1 plus r2 m2. That means, m1 divided by m2 is there in this particular ratio. So, that would also mean that if your comonomer composition is drifting, correspondingly your copolymer composition also will be drifting. So, in order to have a complete understanding of the situation, you need to know how with conversion the copolymer composition changes. So, those things we have actually addressed, and then finally, we also talked about the value of small r1 and small r2, the reactivity ratios. Now, one thing you need to keep in mind here, that when we are talking about reactivity ratio, say we are talking about the ratio r1, which is small k11 divided by small k12. So, k11 is basically the rate constant for the reaction of M1 star, that means the reactive end is M1, M1 star with M1, and small k12 is the rate constant corresponding to the reaction of M1 star with M2. Now, that means the k11 basically is the rate constant for homopolymerization, because at the end of M1, at the end of the chain you have M1 star and that is reacting with M1. Now, you might ask this question without going into the copolymer. If you are looking at only, so we are talking about K11, so we are talking about the homopolymerization of monomer M1 or monomer 1. So, why not just take the monomer 1 in absence of monomer 2 and do a homopolymerization, determine the rate constant that you can use in this copolymerization system and take the value of K11 divided by K12, K12 you have to determine, and then this ratio is R1, but that will not work. The rate of homopolymerization of a particular monomer, if you are taking in isolation, that will be something. In present of another monomer which can copolymerize with it, then the rate of homopolymerization may change. So, whatever rate of homopolymerization you get in normal situation in absence of another monomer, that is not the same as the rate of homopolymerization that you get in presence of the other monomer, and that is why these values of R1, R2, these values you have to determine for specific copolymer system, and you have to determine from this real system in which both the monomers are present. That is the idea here. Now, coming to the point that I wanted to discuss today, it is about the microstructure of the copolymer. This is something we had given a sort of introduction of this in the previous class. So, we will again do the introduction here. So, it is like we are trying to find the sequence length distribution of whatever monomer has gone in. So, if we are trying to find, so you have monomer M1 and monomer M2 that have gone into the copolymer. So, my question then is, what is the number fraction of a dyad of M1? That means, M1 this unit together flanked by M2, both sides M2, and then you have M1 in isolation, M1 isolation, and then somewhere else you have only M1 in isolation. Isolation means on both sides there will be M2, not M1. Again somewhere else you have M1. How many such M1 units will be there with respect to the total length of the polymer? That will be the number fraction distribution of that dyad. Likewise, you could look for triad, say M2 or M1 so on and so forth. So, this will then, once we have discussed the microstructure, the aspect of microstructures, the analysis of microstructures, that will then give us a complete picture of the system of copolymerization. Remember, we are not talking about tar polymerization, for example, a copolymerization system where we have more than 2 components. Those things we are not talking. We are talking about the basic principle, the simplest way we could describe this, and yet we do not simplify it too much beyond the necessity, because that will be a sin. So, let us then go to the microstructure, which is the subject of today's topic. Microstructure. Now, consider a sequence or also sequence length distribution. I have already talked about these things and I am writing it down again, because that also gives you little bit more time to think and probably bolster the concept. So, consider a sequence of M1 units. We are always talking about monomer system M1 and M2 that are coming together into the copolymerization. M1 is monomer 1, M2 is monomer 2. So, consider a sequence of M1 units of length x. So, what is the probability that you will have a sequence of M1 units of length x? So, that would mean you start with this. So, you have an M1 unit here. Now, this adds x minus 1 M1 units followed by 1 M2 unit, because a total of M1 units of length x. So, x number of M1 units have to be there. So, when we are looking for the probability, it is the same way that we treat, although the expressions will be slightly different than when we are saying the number fraction distribution of say step polymerization. From there we had, if you recall, quite some time back we talked about this number fraction distribution and weight fraction distribution for step polymers by Flory's statistical approach. And there also we told that how many independent events are there that concern this particular situation, and of course, all those independent events have to happen together in order for this particular situation to realize. And since they are all independent events, their probabilities will have to be multiplied in order to get the probability of this overall situation happening, which means all the events are occurring together. So, that way then. So, what is the number fraction or probability? Number fraction, both are the same in this case. Number fraction of sequences of M of length x. What is the number fraction of that? So, we will write it like this, capital N x subscript 1 superscript. So, that will mean this is the number fraction of a sequence of length x for monomer 1. So, the superscript is for the identity of the monomer, subscript is for the length of the sequence for which the number fraction we are trying to determine, and this full thing is a number fraction of the sequences of length x for the monomer M1. So, this is nothing but P11 to the power x minus 1 into P12. Now, P is basically the probability, P11 is the probability that your M1 star will add M1, that is the probability, that is why it is 1 1. The first number in the subscript indicates the identity of the reactive center, which is this M1 star. Second number indicates the monomer identity. So, P11 means the probability that M1 star will add M1. So, this probability is P11 and that has to be multiplied x minus 1 times. Why? Because M1 star has to add x minus 1 number of M1 units in order for total number of M1 units to be x. So, that is P11 to the power x minus 1. Then that has to be multiplied by P12, because still the event is not complete. After M1, total of x minus 1 M1s have come. So, total number of M1s is x, but after that an M2 has to come, that event is also important. Only then you will have an in isolation and M1 total M1 units sequence length x. So, that event also has to occur simultaneously, and the probability of that event occurring is P12, because it is the M1 star that is reacting. So, this is P1, it is reacting with M2 monomer, so that is P12. So, both the events are occurring simultaneously and both the events are independent of each other. So, they have to be multiplied. So, Nx1 is equals to P11 to the power x minus 1 into P12. What is the probability P11 that M1 star will add M1? This is nothing but rate of M1 star adding M1 divided by sum of the rates of M1 star adding M1 and M2. This is the probability. So, rate of that particular reaction undergone by that reactive center divided by rates of all the reactions that this reactive center could undergo. So, this is P11. What is that? If you recall our analysis from the previous class in the chain copolymerization, we had all this sequence of reactions that were present. So, what is the rate of M1 star adding M1, that is K11 into M1 star plus M1. What is the rate at which K1, so M1 star adds M2, that is K12 into M1 star into M2. So, in the denominator these two rates have to be summed up, because that is all, that is a complete description of what can happen to your M1 star. It can either react with M1 or it can react with M2. So, that will be in the denominator, and in the numerator only the rate of reaction of M1 star with M1. So, that will be then K11 into M1 star into M1 divided by K11 into M1 star into M1 plus K12 into M1 star into M2. Now, if you remember that K11 divided by K12 is R1, and if you put those values here and M1 star actually is going out from here and you divide by K12 on both sides up and down. So, you can write this expression in terms of reactivity ratio and the monomer concentrations, and it becomes something like this, M2 by M1. And there is a certain symmetry in these expressions, in that if you want to calculate P22, again that is the probability that M2 star adds M2. If you want to calculate P22, that is having a symmetry with respect to this, that will be R2 divided by R2 plus M1 divided by M2. Actually, I would not recommend remembering these expressions. If you have a problem, just work it out. Working out is easier than remembering these expressions, then you can make a mistake. If your concept is clear, you can actually determine this very easily. So, this is P22. Similar way, P12 can be shown to be equal to M2 divided by R1 M1 plus M2, and correspondingly P21 has the same certain symmetry, you see M2. So, it becomes M1 here, instead of R1 M1 you have R2 M2, you have R2 M2 plus M1. Okay. Now, let us try to understand what we mean by ideal polymerization, ideal copolymerization. We said the propensity of M1 star and M2 star to add to M1 is the same. So, that is something like this. In these expressions, you say it R1 R2 equals to 1, which is your ideal copolymerization, so called ideal copolymerization. If you put that, it turns out that your P11 is equals to P21 and P12 is equals to P22. What does that mean? P11 equals to P21. The probability that M1 star will add M1 and the probability that M2 star will add M1 are the same. That means, whether M1 will add at the end of the chain or not does not depend on whether at the end of the chain it finds M1 star or M2 star. Same way, this P12 equals to P22, that means the probability of adding M1 star, probability of M1 star reacting with M2 and the probability of M2 star reacting with M2 are the same. That does not mean that all 4 probabilities have to be the same. If all 4 probabilities became same, you will have a perfectly random distribution, which means R1 equals to R2 equals to 1. But in this case, you do not have a perfectly random distribution. Remember that these two are equal, this probability may be 5 times this probability, that is also possible. So, if this probability is 5 times this probability, that would mean basically that M1 will add, so you have a more M1 in the system, but that does not change the fact that probability of addition is the same. So, the reactivity and the probability, that way they are different things. So, in that case also you have a random situation, but not a perfectly random situation. You have more M1, less M2, and then they will be in random management. Okay. So, that is the situation then. Now, let us try to work out some problems related to this. Say for example, you have R1 equals to 5, R2 equals to 0.2. Obviously, these problems are worked out because I want to illustrate the principle, I do not want to derive it sitting here. So, R1 equals to 5, R2 equals to 0.2, let us say this situation. So, this is ideal polymerization situation, ideal copolymerization situation, R1 into R2 equals to 1, but R1 is higher, R2 is lower. So, how does that translate into probabilities? So, your probabilities, let us say small f1 equals to small f2 equals to 0.5, you take both of them in equal proportion, both the monomers in equal proportion. So, this defines your co-monomer feed composition. Now, if you derive the expressions, your P11 is equals to P21 and P12 is equals to P22, you can actually derive those expressions because you know you have your P11 is R1 divided by R1 plus M2 by M1, M2 by M1 you know, in this case it is F2 by F1. So, this is equal proportion, so it is 1, R1 values you know. So, correspondingly you can find out P11, same way you can find out P22, all are in terms of your co-monomer feed composition and your R1 and R2, all these things are known. So, you can find out these values. So, if you find those values, you see indeed P11 equals to P21 and P12 equals to P22, and look at these values here, it is 0.8333 and this is 0.1667. This is what I wanted to tell you, that the propensity. So, you see both M1 star and M2 star, they will add M1 and M2. So, both M1 star and M1 star and M2 star will add M1 with the same probability of course, and they will add to M2 with the same probability, but this probability is 5 times this probability. So, that means both M1 star and M2 star will add to M1 with a 5:1 tendency, or let me make the statement a little bit in a different way. So, both M1 star and M2 star have a 5:1 tendency to add M1 over M2, 5:1 tendency. So, even though these probabilities are equal, they have a 5:1 tendency because your M1 is more reactive. So, 5:1 tendency means obviously more of M1 will go into the system. Now, let us say you are trying to find out what is the number fraction of this dyad M1 M1. So, the number fraction of this dyad is n you say NX1. So, X is basically 2 because this is diode. So, here you are talking about N21 and your expression was basically this P11 to the power x minus 1. So, this will be P11 to the power 2 minus 1 into P12. So, that will be equal to P11 to the power 2 minus 1. So, P11 into P12 and these values if you put here. So, this is 0.8333 into 0.1667. So, that becomes 0.14. So, basically you have 14% diode in the system. Now, if you are considering something else, let us say you are talking about an alternating polymerization, copolymerization, R1 equals to R2 equals to 0.1, both of them are low, but they are not 0. So, that means there is no perfect alteration. If there is a perfectly alternating system, then both the monomers will go in equal proportion to the copolymer and in a perfectly non-random fashion, means M1 M2, M1 M2, M1 M2, this is non-random, perfectly non-random fashion, and regardless of what is the feed composition of the co-monomer, you will have 1:1 both the monomers going into the copolymer. So, whether you take 80 mole percent M1, 20 mole percent M2, or whether you take 80 mole percent M2 and 20 mole percent M1 will not matter. If both R1 and R2 are 0, both of them will go in 1:1 proportion into the copolymer and they will go like M1 M2, M1 M2, M1 M2, that is the thing. Now, let us say R1 and R2 both are low, but not equals to 0, then what happens? This is close to an alternating situation, but not close enough, not perfectly alternating. So, you might reasonably ask what is the proportion of a system where you have only M1? It will be 100% if it is perfectly alternating, because M1 M2, M1 M2, there is no diode like M1 M1, there is no triad like M1 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 if R1 equals to R2 equals to 0, but in this case you will have diodes, you will have triads. Nevertheless, the proportion will be very low because it is close to being perfectly alternating, but it is not perfectly alternating because R1 and R2 are very low. So, let us find out from this kind of microstructure analysis you can have the answer to all these questions. So, R1 equals to R2 equals to 0.1, let us say this, then your P11 if you are putting that thing here. So, P11 equals to P22, this comes as 0.91 and P12 equals P21, that comes as 0.909, and let us say you have taken F1 equals to F2 equals to 0.5. So, then the question is what is the sequence length distribution for a single M1 unit. So, M1 unit, so that will be N11, so single unit, and this is the identity of the monomer. So, this is 1 N11, so that is nothing but P11 to the power x minus 1. So, this is 0, x is 1 in this case because single unit into P12. So, that will be nothing but 0.909. Okay. Now, so this is the single M1 sequence, this is the this much percent of single M1 sequence. What is the situation of a, let us say, M2 unit which has a single unit present, that means only M2 and flanked by M1s. So, that will be N1 2 because this is the second monomer, 1 is the sequence length. So, that will be P22 to the power 0 into P21, that will be also equal to 0.909. So, the propensity to have only one M1 unit isolated is 0.909, only one M2 unit isolated 0.909. So, basically you will have M1 M2 units, propensity to have M1 M2 units 90.9%, something like that, not 100% because this is not perfectly alternating situation. So, if you are looking for a diode, for example M1 M1 or M2 M2, you can actually work it out, it will be 8.3%, and if you are looking at, say, for example, a triad M1 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 and M2 M2 M2, I mean here it is a special scenario where R 1 equals to R 2 equals to 0.1, that is why these are equal, these may not be equal depending on these values, but I am trying to illustrate an important point here. You see that they are tending towards alteration. M 1 M 2 units, the number fraction distribution is around 91%. If it was perfectly alternating, it will be 100%, but it is not perfectly alternating because this R 1 equals to R 2 equals to 0.1, this value is not 0. If it was 0, then M 1 M 2, the probability of having M 1 M 2 sequence will be 100%, but here it is not 0. So, it is tending towards alteration. So, around 91% you have. And what about the rest of the things, say M 1 M 1, you may be surprised, but M 1 M 1 or M 2 M 2, say dyads, you can find 8.3%. So, out of the total sequence distribution, the total number of M 1s that are present in this particular length of the polymer on an average, out of that 2 of them are together like M 1 M 1, again M 1 M 1, again M 1 M 1. Out of the total number of M 1s, the percent distribution, the number fraction distribution, it gives you 8.3. So, what is the number fraction distribution? It is the total number of those sequences, say M 1 M 1, how many M 1 M 1 sequences are there, divided by total number of M 1 units, something like that. So, that is the number fraction distribution, total number of this is there, total number of M 1 say 100 is there. So, how many of them are distributed like M 1 M 1 units, that is your number fraction distribution, that is what we are talking about all through. So, you see that 8.3% of M 1 will be distributed as M 1 M 1. So, this is not perfectly alternating, and when you go to M 1 M 1 M 1, it is only 0.75. So, when you go to triad, tetrad, still certain percent will be present, but that amount will be very, very low because it is going towards close to being alternating, but not close enough, 90%, not 100%. Okay. So, finally, we will finish this with another problem which I hope will strengthen the concept if at all certain questions are remaining. So, let us say acrylonitrile, the structure in this case is not important. You are doing a copolymerization of acrylonitrile, say you are saying this is monomer 1 and R 1 is 0.9, you are copolymerizing this with 0.25 mole fraction of vinylidene chloride. This is monomer 2, R 2 equals to 0.4. Now, which one of them you take monomer 1 or monomer 2 does not matter, correspondingly the calculation will change, as long as your concept is clear you can work it out, and structure in this case does not matter. Okay. So, this is a copolymer system, your comonomer feed composition is given. So, you have 25 mole percent of monomer 2 and rest of that, that is 75 mole percent of monomer 1 that is present, and correspondingly these are R 1 and R 2 values. Okay. So, now the question is what fraction of monomer 1 sequence or acrylonitrile sequences contains more than equal to 3 acrylonitrile units. So, that means you have to find out what fraction contains 1 unit, what fraction contains 2 units, and then you have to subtract that from the total. Then you can find out what fraction contains at least 3 number of monomer 1 or acrylonitrile units in this case. So, then if you go ahead, so that will be nx 1 general term for monomer 1 x number of sequences, it will be p 1 1 to the power x minus 1 into p 1 2. So, in this case your x, let us say you take n 1 1, so that will be equals to p 1 2. You can calculate these things, say for example p 1 2, I will just calculate one of them and leave the rest for you, 1 plus R 1 into m 1 by m 2, and you can find this from this ratio. So, you know the ratio because 0.25 mole fraction is there. So, this 0.25 divided by 0.75 R 1 value is there. So, p 1 2 will be according to what I have calculated here 0.27. So, you can put that value here, that will be 0.27. So, 27%. So, 27% of total monomer 1 is present as only unit, single unit. What about 2 units together? that will be P11 to the power 1 into P12, and you can actually calculate this, but I will not show you here. Take it as homework. This into 0.27, this comes as 19.71%. So, you just do a total of this, I think it will come something around 46.71%. So, then how much fraction contains greater than or equals to 3 acrylonitrile units? That will be 1 minus summation of these two. So, you are taking 1, you could take 100 also. So, if you take 100, then you have to take 27, if you take 1, that will be taking 0.27 plus 40, so plus 19.71. So, 100 minus that, so that will be 53.29%. So, that will be your answer. And then if you are asked the next question, the final question, if I am asking what is the feed composition such that the copolymer composition does not vary with conversion, or what is the feed composition such that during copolymerization the composition does not change, that is azeotropic composition, azeotropic copolymerization, excuse me, that will be valid here because R1 and R2 both are less than 1. So, you can use the formula, or you can derive the formula also if you do not remember. M1 by M2 equals to R2 minus 1 divided by R1 minus 1, put the values R2 and R1 and you will get 0.6 divided by 0.1, so 6. So, if you take 6:1 mole ratio of acrylonitrile to vinylidene chloride, you will get a copolymer with exactly the same composition, that is 6:1 acrylonitrile to vinylidene chloride will be present in the copolymer, because that is the azeotropic composition of the comonomer mixture. So, with this we come to the end of this particular class, and as far as I am concerned, I have discussed satisfactorily whatever principles I wanted to. I hope you will agree with me about the copolymerizations of two monomer units, chain copolymerization. We did not talk about step copolymerization, and the status will remain so in this particular course. So, what we are going to talk about in the next class is leaving chain polymerization, and I am going to talk about why it is leaving and why it is important in terms of the kind of compositions of the polymer that you want to get, in terms of the molecular weight of the polymer that you want to get, and in terms of the molecular weight distribution of the polymer that you want to get, and the industrial ramifications of that could emerge out of that. And that is why these kind of leaving chain polymerizations are important. Till then, thank you and goodbye.